I'd like to show you this relationship I have found between the building parts, or the isosceles triangles that are rotated to create a regular hexagon, and these highlighted points on this series of circles. What I'd like to do is unroll the hexagon to show you where the formula 1/2 times the height of one of the building block triangles, which we're going to call the apothem, times the perimeter comes from, and how it's related to the area of the hexagon itself. So I'm going to rotate this first triangle through point number 1 by 120 degrees clockwise. I'm hoping that it lands right here. And it did. This is good news. I'm going to rotate this second building block, this second triangle in the regular hexagon, around point number 2 by 60 degrees clockwise. I'm hoping it's going to land right here. This is good news. I'm going to rotate the third triangle around point 3. I'm going to rotate it 120 degrees. And I'm hoping it lands right next to the other. So I'd like a series of triangles that will represent the unrolled hexagon along this x-axis. So as you'll notice, we're going back and forth between 60-degree rotation clockwise and 120-degree rotation clockwise. And the centers of rotation are related to this series of triangles. So we've done 1, 2, and 3. We're going to rotate the fourth one around point number 4. And I may have just said series of triangles, series of circles, and their intersection points. So that's 4. We want to now rotate the fifth one through this point, not by 60, but by 120 clockwise, hoping it'll land right here, which it does. And then this 1, 2, 3, 4, 5, this sixth one, I'm going to rotate through this point by 60 degrees clockwise and see where it lands. And here I have represented the 1, 2, 3, 4, 5, 6 building parts, or 6 triangles that can be constructed to create, by reflection or by rotation, this regular hexagon. And now the apothem is drawn into the hexagon, and we may as well have the circle that circumscribes that polygon in there as well. The sides of each of the building block triangles are radii of the circle. They're also called radii of the polygon. And what I'd like to do is build a triangle around these 6 triangles that came from the hexagon. And I want it to be an isosceles triangle. So to do that, I'm going to build a segment across here, and I'm going to find the midpoint of that segment. And I'm going to create a triangle that has a base the length of the apothem, and has, I take that back, it has a base the length of the perimeter and a height the length of the apothem. So for the moment, let's change the color of this triangle to something a little bit lighter. And what we have here is a representation of a triangle that has a base equal to P, the perimeter of the hexagon, and a height equal to A, the apothem of the hexagon. It is a triangle represented by the formula 1/2 AP. We also have a hexagon that can be represented by the formula 1/2 AP. And we can create a polygon on the vertices of the unrolled hexagon that will have the same area. It is really constructed just of 6 equilateral triangles with side length equal to 1. And we can change the color of that polygon. Let's see something a little bit more different. Maybe we want to brighten up a couple of these. These figures are all related. That's better. So these polygons are all related. The pink hexagon has the same area as the purple figure that is created by combining 6 equilateral triangles with the same side length as the hexagon. And they have the same area as the green triangle. It has base equal to P, the perimeter of the hexagon, and height equal to A, the apothem of the hexagon. So the formula 1/2 AP used for finding the area of a regular hexagon is created simply by multiplying the heights of each of the building block isosceles triangles, in this case the hexagon, which has building blocks that are not only isosceles but also equilateral. An additional exploration calls for rotating the purple polygon through the first point of rotation, 60 degrees counterclockwise, and then creating a new polygon captured here. And then rotating this new polygon, which is made of 5 triangles, so original -1, around this point, 60 degrees counterclockwise, and then capturing this polygon, which is made of now 4 triangles, and rotating it 60 degrees around this point, and then capturing this polygon made with 3 triangles and rotating that through this point 60 degrees, and then capturing these 2 and rotating these 2 around this point 60 degrees, and then capturing this one last polygon, the leftover bit, the sticky outy piece, and rotating that one leftover piece around this point 60 degrees to recreate not just the original hexagon, but also quite an interesting figure or series of figures where we can highlight any number of additional interesting places to study. So the 6-pointed star that I've just outlined should have an area that's twice as large as the original hexagon. Cool. And we can see that it does. It has area 5.2 units, whereas our original hexagon has area 2.6 units.